That's a little better. Okay. Is my screen visible?
Yes.
Okay. So as a reminder, this is the workshop link containing links, for example, to the notes. So we're going to need new volunteers to take notes for the second session of the day, ideally 2 if we can get it. So this session is, well, it's a 90-minute session. So there'll be a 30-minute presentation and a full hour for discussion. I can't see any messages, so I hope the screen sharing is still going okay. So the title of the talk is AirAssembly, a low-level language for encoding AIR of computations. Our speaker is Bobbin, who started working with Starks about a year ago. So his projects include the GenStark library, which is an implementation of the Stark prover and verifier, as well as the AirScript and AirAssembly languages, and Distaff VM, which is a Stark-based virtual machine. And prior to his crypto work, Bobbin was a software engineer, a startup founder, and a management consultant. So please, Bobbin, take it away.
Thank you very much for the introduction. And hi, everyone. Let me start sharing my screen. Let's see. All right, you guys should be seeing my screen, and now we'll start the presentation. Okay, can everybody see the first slide?
Yes.
Okay, and I'm guessing my sound is coming through okay?
Yep.
All right, so let's start. So as Justin mentioned, so my talk today is about AirAssembly. It's a low-level language for encoding AIR of computations, and this is primarily used in Starks. And the things I would like to go over today is kind of just basics of AIR arithmetization and what exactly it means. I think a lot of you already know a lot of this, so it might be somewhat repetitive, but it's good to set the stage because the AirAssembly kind of mimics what what you need to understand about AIR and like tries to describe a lot of that. So once I go through AIR, we'll go through the language itself, and then if there's enough time, we'll go through a simple example of how AirAssembly can be used to encode a simple computation. So first, just to set the context, we can think about computations in 2 different ways. There are circuit computations and machine computations. And again, a lot of this is going to be very familiar to you guys. And this is not going to be an exhaustive comparison. So like I'm going to be missing a huge kind of nuances here. But in general, you can think about the computation in these 2 ways. And the representation for circuit computations is arithmetic circuits. It's circuits. It's a circuit that takes some inputs and kind of inputs propagate through the circuit, and you get some outputs. With machine computations, you represent them, as a transition function, where you have some computation state, and you repeatedly apply the same transition function to that state, and for a number of steps, and then you get to some answer. And in terms of arithmetizations, R1CS is the one that is used for circuit computations, and AIR is the one that is used for machine computations. And there are different types of trade-offs between the 2. And here again, I'm just capturing a tip of the iceberg here. But for example, R1CS, it's fairly easily, you can reduce general purpose computations to R1CS fairly easily. You can compose the constraints fairly easily, which is not necessarily the case for machine computation of AIR. So, but because AIR is represented as a succinct transition function, you can represent very efficiently some specialized computations, and the proving time and verification time could be much faster than kind of for R1CS based systems. And writing kind of circuits or constraints directly in R1CS or in AIR is fairly challenging. So there are higher level languages that exist to make those tasks simpler. So there are a bunch of languages for R1CS. I've just mentioned here 3, but I know there is many more than that. And for AIR, there are AirScript and AirAssembly. Those are the ones that I'm aware of, and both of them actually were created by me, but they allow you to more easily represent AIR for Stark proofs. And where they're used, kind of like you guys already probably know all of this, but R1CS is heavily used in kind of pretty much all Starks, while air is, as far as I know, is only used in Starks. And by Starks, I mean very specific, it's not just all transparent proving systems, but kind of this specific implementation that uses air as a underlying arithmetization technique. All right, so with this kind of like, let's jump into air specifically. And I think kind of underlying concepts are fairly simple, and there are very few of them. But once you understand how they work, I think it's very easy to think how you can convert a program into an air representation. So let's start out. The first one is kind of the concept of a computation state. If you think about a computation as, for example, being run on a processor or a CPU, CPU has registers, and you can think about the computation state as a state like the values that those registers have at a given point in time. That's a kind of conceptually very useful way to think about a computation from the air standpoint. Now, the next thing is the execution trace. So if you take and capture the state of a computation at every single point in time when it runs through the kind of its execution, that's going to represent your execution trace. And basically, the way to think about it, it could be as a two-dimensional matrix where your column is a given register and your row captures a value of a register at a specific step in the computation. Then your transition function, what it really does is it takes your computation from one state to the next. So it takes as an input the current state and it produces as an output the next state of the computation. And you repeat the same function over and over again until you get to the end. And then your transition constraints in this kind of context is that they take two consecutive states of the computation and apply some a function to them. And if the output of that function is all zeros, that means the constraints hold. If the output of the function is something else, then the constraints do not hold and the computation is not valid. And the last thing is boundary constraints, and those constraints allow you to specify, at a given point, at a given step in the computation, a given register has to have value X or Y or whatever. And this is a way for you, for example, to check if at some intermediate step in the computation, a given value is equal to some predefined value, things like that. Underneath kind of this, it's in reality, transition constraints and boundary constraints are really the same thing, but I think conceptually it makes sense to think about them separately. Right, so let's talk about execution trace in a bit more detail. So as I mentioned, it's a set of registers that you apply a transition function to generate values throughout the execution, but it's not necessarily 100% correct. So you can think about it as two separate parts of the trace. So there's dynamic registers that get generated by the transition function, but you can also say there are static registers that can be generated outside of the transition function. And one way to do that is to have a very simple, succinct function that can generate all the values for those registers. You don't need this transition function, but you can have something simple. As an example, you can have cyclic registers where a set of values gets just repeated over and over again, and that can be represented as a very simple polynomial. Or another kind of what I call a holy register, where you have another function, but the function describes kind of a sequence of values, and the sequence of values is spread through the entire execution trace. You don't necessarily care what happens in between, but you know that the new value appears in the trace every 4 steps. And these two concepts, they're fairly simple and they can be represented succinctly, but they're pretty powerful in the ways you can combine them to get like a shape of a register where you can have some values shifted in a given register, or like repeating after kind of different types of periods and so forth. Some considerations about execution trace is that it must be a power of 2. The length of the trace must be a power of 2. You can make static registers either public or secret, and the field in which you work must have high orders roots of unity. So kind of updating the definition of a transition function. So in this kind of slightly expanded model, a transition function takes the current state of dynamic registers, the current state of the static registers, and produces the next state of the dynamic registers. So that's how it works. And this may seem like, as I mentioned, you need to apply this function, the same function, over and over again to the computation state to get to the end. And it may seem fairly limited because it's only one function, but in reality, you can apply this concept of arithmetic switching, where you would say, based on the value in one register, in the static register, I want to apply either one function or the other. And you kind of get to select multiple options of which functions to apply. And it gets very powerful. You can do a lot of things with it. For example, the dstuff virtual machine that I'm working on allows you to have a separate transition function for each instruction, so that you can choose which instruction gets executed in a given state, but every instruction is represented by a different transition function. And some more considerations about transition functions. You can use all arithmetic operations in them. The degree of the function, which is important because it translates into the complexity of the computation, the proof generation time, and the size of the proof. It grows every time you raise a register to some power, or when you multiply to register. And again, I haven't been perfectly honest here, because in reality, you can have this long-range transition functions that take more than just 2 consecutive states. For simplicity, I'm keeping it to as a 2 consecutive states. The function produces the next state given the previous state, but you can think of a function that takes, let's say, 2 previous states and produces next state. That, a Fibonacci sequence works in the same way, for example. All right. So next, let's expand our definition of transition constraints. So now a transition constraint, in addition to just taking 2 consecutive states of the dynamic registers, it will take also a state of the static registers, and then it will produce the constraint evaluations that, if the computation is valid, they should all be 0. Frequently, for a simple transition constraint, what you do is you take a state, apply transition function to it, and then subtract that from the next state of the computation. And that could be, if the computation is correct, that should work out to all zeros. But you can actually make things more complicated. You can apply different functions, like let's say you apply a function to the current state and apply a different function to the next state, and then you subtract one from the other to get constraint evaluations. And in fact, for example, in the rescue hash function, they are using a more complicated function that allows you, more complicated definitions of the transition constraint, where the function is not as simple as just abstracting application of a transition function from the first state from the second state. And some considerations about transition constraints. Division is not allowed, but it can be emulated. Degree of the transition constraint may or may not be the same as the degree of the transition function. In reality, what matters is not the degree of the transition function, but the degree of the transition constraint. So that's what you want to really look out for. And then the same as I mentioned, long-range transition function, you can expand the definition of transition constraints to take more than just 2 consecutive states. They can look forward or look backward in the computation. So there is a lot of flexibility, and that flexibility comes with an additional kind of mental complexity, but you can do a lot of things with it. All right. Let's see.
Can I just ask a question?
Yes, of course.
This seems similar in some ways to the Plonk arithmetization, except, the Turbo-Plonk one, except that you don't have the permutation argument. Have you sort of considered those connections and whether it might be possible to have a language that sort of generalizes both kinds of proof system?
I have heard similar comments before, but to be honest, I have not looked into it in detail, so I would not be able to answer it like intelligently about that.
Okay.
Okay, so let's dive into the AirAssembly language. And kind of the goals of the AirAssembly language is really kind of just to capture what I described in the last few minutes. We want to have logic for generating the execution trace. We want to have logic for evaluating constraints, or generating constraint evaluations, and I want to have some logic for interpreting inputs. So those are the 3 goals. And the way I think about AirAssembly and how it fits into kind of like the overall toolchain model and why it's called a low-level language is that it is intended to be kind of intermediate representation. So like there would be a high-level language, and AirScript is an example of that gets compiled into AirAssembly. And then a Stark prover or a verifier would be able to read AirAssembly and generate proofs based on that, or verify proofs based on that. And then that, it doesn't have to be, GenStark is one implementation of that I've written myself, but it doesn't have to be like that. Other people can write a Stark prover and verifier in WebAssembly or in Rust or in any other language. And as long as they understand how to read AirAssembly, you can, in theory, generate and verify proofs on different proving systems. And then to expand this even further, it doesn't have to be AirScript that gets compiled into assembly. Somebody can come up with a different language that gets compiled into AirAssembly, more specialized or for better than AirScript and so forth and so on. So this is my ideal state of the world, where there's going to be a bunch of languages that get compiled to AirAssembly, and there will be a bunch of Stark provers and verifiers that will be able to understand that and verify and generate proofs. Now, before going into the structure of AirAssembly modules, I just give you a preview of the syntax. And the syntax is extremely simple. I looked at took the inspiration from WebAssembly, where all the the underlying syntax is S expressions. You have an operation that applies to operands. The language is not, AirAssembly itself is not meant to be easily readable by humans, but it is very easy to parse and has a very compact representation. In terms of what you have available in the language, there are 3 data types: scalars, vectors, matrices. There are 8 arithmetic operations. All of these should be familiar except for maybe product operation, which I'll explain in a second. And then there are, you can work with vectors, get a slice of a vector or specific value. You can abstract away some common arithmetic expressions into functions and then call on them. And then you have load store operations that allow you to load the state of an execution trace, for example. And I'll go through this in a bit more detail in a second. So in terms of data types, so there are scalars, vectors, and matrices, as I mentioned, and they're just what you would expect them to be. Very easy to. This is how, on the left-hand side here, is how you write a scalar in AirAssembly, and this is how you write matrix and so forth. So fairly intuitive. Arithmetic operations, work as you would expect arithmetic operations to work in finite fields. The one thing that I want to mention is that you can apply arithmetic operations both, not only to scalars, but to vectors and to matrices. And in that case, it produces element-wise operations. So you can add 2 vectors, and it would be just the element-wise sum of the elements in the vector. And the output would be another vector. And this works for pretty much all other arithmetic operations. The product operation works slightly different. It works differently based on what operands are. So if you do a product operation with 2 vectors, you get a linear combination. If it's 2 matrices, you get a matrix multiplication. If you get you can also compute a product of matrix and a vector, and that's a matrix and vector multiplication. And this operation is useful, for example, in Poseidon or rescue hash function. You have this MDS matrices, and they can be very compactly expressed using this operation multiplication by those matrices. So you don't have to write complex expressions to do that. Vector operations are very straightforward as well. You can extract an element from a vector, and then you get a scalar, or you can get a part of the vector by using a slice operation. So this covers pretty much all the syntax. So as I mentioned, the language is very, very simple. So there is not a lot of complexity behind it. But all of the syntax allows you to build an AirAssembly module. And an AirAssembly module can contain, it's basically a self-contained computation, or actually several computations. And I'll go through what it consists of. So the first thing is that you have to define your field. Right now, only prime field is supported. So you specify the modulus of the field, and it's as simple as that. Then you can define some common constants that could be used within the module, and those could be scalars, vectors, and matrices. Then you can specify functions, which are just encapsulation of common arithmetic expressions that you will be using inside of your computations, and the transition functions or transition constraints. In this example is MIMC round function. I'll explain how it works a bit later, so don't try to parse it through it right now. And then you have within each module you can have multiple components, and the component is a specific computation. So you can think about it as like air for a hash function could be one component, or air for verifying a Merkle proof can be another component, and you can have many components within a module. And each component has different transition functions and different constraint evaluations and so forth. But the first thing that you define inside the component is your static registers. So here, there are some ways. Again, don't try to parse through it. I'll explain this in a bit more detail in a couple of slides. But basically, this is how you would define a set of static registers. You define a trace initializer is basically how you read in the inputs and translate them into the first row in the execution trace. And after you have the first row initialized, then you can start applying the transition function. So this is the next thing that basically it takes one row, or actually could take more than one row, but I'll get to it in a second. And then produces the next state of the computation. And lastly, you have your constraint evaluator, which is describes the constraints that you want to apply to the execution trace using the same type of statements, arithmetic statements. So in terms of how this gets executed, so you have some inputs, and the first thing that happens is that you build a static execution trace for the static registers. Then you initialize the trace and apply a transition function, and you get the entire execution trace table. And then you evaluate constraints on the built trace table that you have built using the transition function and trace initializer and the static registers before. It doesn't go further than that. So like this is basically what AirAssembly does. Now there is a bunch other steps that need to happen to get proof from this, but this is the building blocks of the proof that then a start prover or verifier can take from this one. In this case, it would be a prover that would take this constraint evaluations and execution trace and build a start proof out of it. Now, just to give an example of how the static registers work. So, let's say I have this 4 static registers defined. 2 of them are going to be input registers. There is a mask register and there is a cyclic register that will repeat a set of values. The input registers, you can provide some inputs for them, and they will spread them out across the execution trace. In this case, I decided to get a bit fancy, so I have 2 inputs where both inputs are public. And this input 2 depends on this input. So for every input that we have for input 2, or actually for every input in this input 1, we'll provide 1 or more inputs for input 2. And then this input has to be, for every value that we provide for this input, there has to be 4 steps in the execution trace created. So the way this actually translates, you can think about this as register S1 or S0 and S1. These are the 2 inputs. So if we provide 1 and 2, it would generate an execution trace of 16 steps long, 16 steps because there is 4 values provided for register 1, this input, and each input has to have 4 steps. So 4 times 4 is 16. And here, basically it will form cycles where this is the cycle for this first input. And then you will have 2 inputs provided for in the second register for this. So like 3 and 4 will be provided, and 5 and 6 will go here. And then the inverted mask just says when there is a value in the input 1, just put a 0, and otherwise put a 1. So it just like kind of masks the second input. It is useful to apply in arithmetic switching, if you want to apply different functions to different steps. And lastly, the cyclic register, all it does is just repeats the set of values 1, 2, 3, 4, 4 times throughout this execution trace. Now, one last thing before I jump into the example of how you can write a simple, we describe a simple computation using AirAssembly. So this is how you would access the execution trace. You have this load instructions that allow you to load the given state of the execution trace, and the load instruction, load trace instruction takes a parameter that says, if it's a 0, it's a current step, 1 means next step, and -1 means a previous step, and you can go back and forth in the execution trace to load different steps. So like if I wanted, for example, to load the current steps, I would say load trace 0, and it would return the current step. If I wanted to get a specific value, because every state is a vector, I could just get a value out of this vector, and it would give me 6. All right, I know that was a lot. It's even though the language is simple, it's difficult to understand within 15-20 minutes. So let's go through a simple example, which I think everybody will be familiar with. So MIMC arithmetization. This description of a MIMC function should be familiar to pretty much everyone here. You just take the current state, you cube it, and you add the round constant to it. So this is our current state, this is our round constant, and this is our next state. What this translates to in terms of air, you have 1 dynamic register and you have 1 static register. And if we wanted to see how an execution trace for this would look like, so let's say we start with our input value would be 3. For simplicity, we'll just use 1, 2, 3, 4 as round constants, and then we'll just say it's going to be 64 steps, even though in reality it should be more than that. And then we'll use a very simple 32-bit field again for illustration purposes. So if we apply kind of the description of the transition function to the input value 3, we'll get something like this. And the way this got generated is that the initial input 3 goes into our dynamic register. Well, even before that, the static register execution trace is just repeating of these 4 values all the time. So they get repeated. Then the initial step that gets initialized to 3 based on our input value. And then we start applying a transition function, cubing the initial step, adding round constant, and then cubing initial step, adding round constant. And then that's how we get to that final value at the end. Now, this is how AirAssembly for describing MIMC computation looks like. And again, it probably looks a bit intimidating, so let's go over through this very quickly, line by line. So we define our prime field, the field that we'll be working with. We define a constant 3, which we'll call alpha. And this is going to be the power to which we raise our current state. I didn't have to define it here. I could have used the inline inside the computations, but just for illustrative purposes, I put the constant definition here. Then we define a single function, which would be our MIMC round function. It produces a vector of length 1. It takes as a parameter the current state, which is a vector of length 1, and it takes a scalar, which is a round key. And then what it does to it, it loads this parameter, takes the value of the parameter, exponentiates it into our constant alpha, and then adds a round key to it. That's all it does. And then this is the description of the MIMC component within this module. It uses 1 dynamic register, has 1 constraint, and it runs for 64 steps. It uses a single static register, which is just a repeating cycle of 1, 2, 3, 4. And then the initializer just takes the seed value and kind of outputs the vector with a single register that has that seed value as the only value in that vector. And then the transition function is very simple. All we do is we load the current state of the execution trace, load the current state of the static registers, and get the only value out of it. And we call our MIMC round function using this as parameters. And then the constraint evaluation is very simple as well. What we do is we basically, like, this line is identical to this line, so we basically call our transition function on the current state, and we subtract that from the next state of the computation. And if that value is to 0, then the computation should be valid. So this is a very trivial computation. MIMC is not difficult to describe, but you can describe a Poseidon hash function or a rescue hash function using the same. And in fact, in the libraries that I have written for GenStark and AirAssembly library, and there are examples of how you would encode, let's say, a Poseidon hash function, a rescue hash function, or even a Merkle proof verification in AirAssembly.
Can you explain? Can you explain why you needed to repeat the expression where you're calling MIMC round?
Why did I need to repeat these expressions here?
Yes.
So these are used for 2 different steps within the computation. So this transition function is used to generate the initial execution trace. The evaluation is the constraint evaluation that is used once the trace is generated. And you apply this kind of function to the already built trace. Now, they're the same in this context, but they don't have to be the same. It's just the MIMC computation is fairly simple, and it's the same transition function that you evaluate the constraints by applying a transition function to the current state and then subtracting it from it.
So if you wanted to express non-determinism, then those wouldn't necessarily be the same.
It's not necessarily non-determinism, but for example, as a rescue hash function, your transition function and your constraints look very different, so it would not be the same in that case.
Right, when you're computing the inverse, yeah, okay.
Yeah.
Got it.
All right, I think that's pretty much all I had, and happy to answer any questions. I haven't been paying attention to if there were any questions while I was speaking, so if there were, just ask them.
Thank you.
Thank you.
Thank you. Yeah, so there was a lot to take in. One high-level question is, can I also think of this as a kind of arithmetic circuits is a very special structure where kind of where there are levels I that have the same structure, except that they take additional constants as input, and you're kind of describing that arithmetic circuit and also like some additional machinery to prove it efficiently using a stack?
I think you can probably convert this into an arithmetic circuit. I don't see why it shouldn't be possible. I'm not sure if that would be the most efficient way to build an arithmetic circuit out of this. It might not come up with, and because there is, like when you build air, you kind of assume that you have to have the same function repeating all the time.
Yeah,
so you have to put in.
I understand that, but so it's kind of,
Yeah.
you can see a stack as a proof system that allows you to prove very special arithmetic circuits, not any arithmetic circuits, but only a very special one. And that's the one that you also kind of generate here.
Well, so you can express, so like using this concept, like if I go back in my presentation to, let me see, where was it? Yeah, so you can actually use air to represent any computation. It doesn't have to be specialized. It's just it becomes much more efficient when it's specialized and you have this repeating structure. But using this technique of arithmetic switching, you can pretty much express any computation. It's just not going to be potentially as efficient as some other representations.
Yeah, that makes sense.
So can you say a little bit about the output of AirAssembly? So my understanding, which is that it outputs, a programmer expresses a computation in the language, and then it outputs an execution trace matrix, which like a Stark prover can then use in a straightforward way to generate a Stark proof. Am I understanding correctly?
Yeah, so let me kind of give a concrete example. So GenStark is the library that I wrote that understands AirAssembly. So what it does, it reads in the AirAssembly source code and it basically parses it, and it uses the source code. It translates the source code into a combination of JavaScript and WebAssembly, and it kind of transpiles it. And it's not that difficult to transpile because of the simple structure of AirAssembly. But you actually get an executable code that is, let's say, JavaScript in that case. And the GenStark library runs the JavaScript to generate those, execution trace and then to generate constraint evaluations. And then those get fed into the generic machinery of generating Stark proof. So actually one thing that I could show as well how this would work is, if you think about how Starks work in general, let me just go to one slide that I didn't show. So Starks work like this. So you have inputs, you generate execution trace, and then you get constraint evaluations. And then after that, there is a bunch of things that happen, like you compose those things into a composition polynomial, and then you apply the low degree proof, the Fry protocol, to generate the actual proof and so forth. And the thing with Starks is that these two steps are computation specific, like how you generate the execution trace and how you generate the constraint evaluations is specific for each computation. And those would be different for a hash function versus a Merkle proof verification or whatever else. But the other parts, the composition polynomial, how you kind of combine them together, how you run kind of low degree proof, they're really the same. They don't depend on a specific computation. You can reuse the same machinery for, as long as you have the execution trace and constraint evaluations generated, everything else remains the same. So the kind of the idea behind AirAssembly is that it tells you how to generate these two things, and then you have your Stark prover or verifier that can take the outputs of whatever you use to generate using kind of description of AirAssembly, and then you apply kind of the other steps that you need to generate the Stark from.
I see. Is there, so, one benefit of the approach in Starks, and some other proof systems have this too, but not all, is it can avoid pre-processing, and that's like the kind of the point of restricting to these very uniform computations where it's the same transition function applied over and over again. Is there tooling right now to let the verifier avoid this pre-processing, that is not looking at a full constraint matrix of the execution or something like that?
Yeah, definitely. I mean, with Starks, you don't actually do any pre-processing. So the idea is that, let me go to the MIMC computation. So both the prover and verifier will read this description, but this description is very, very simple. This is, and even for more complicated systems, a description of, let's say, a Merkle-proof verification or something, it's you know, like hundreds of bytes or maybe kilobyte of information. Maybe, you know, for a very complicated computation, it would be reduced to a few kilobytes. But both prover and verifier read the same thing. They don't need to read anything else. And then the prover generates this execution trace and the constraint evaluations and kind of generates the entire table, and they need to consume a lot of memory to do that and then generate a proof. But the verifier, they only need to evaluate constraints at specific points in the execution trace that the prover sends them as part of the encoding in the Merkle tree, and you know, it's part of the start, where you have, like, let's say, you know, 40 or 80 points that you send to the verifier that they need to verify that constraints evaluated correctly on those points. So the verifier only needs to run this computation on 80 points versus like a million points or like many millions of points that the prover does. And that's inherently very, very fast and succinct. So using the same definition, both for prover and verifier, you kind of like, prover spends like seconds or minutes generating the proof. The verifier verifies them in like milliseconds or less.
Great. And is there, I guess one approach that I believe is available open source also that's similar is you would write like a TinyRAM program, which is the same idea of a uniform computation. And then I believe that, you know, there are front ends that will basically do similar things, but starting from a TinyRAM program instead of an AirAssembly program. Do you have a sense of the pros and cons of, you know, using the AirAssembly language that you've designed?
Yep. So I would say TinyRAM is potentially slightly different. So you would potentially use AirAssembly to define constraints for TinyRAM as itself. So like TinyRAM, somebody had to write constraints that express how TinyRAM program works, and not specific program, but the processor, the TinyRAM processor works. And those constraints could be encoded in AirAssembly. So like, I'm not using AirAssembly for that, but as I mentioned, I'm building this dstuff virtual machine, which is kind of like a simplified version of TinyRAM in some ways. It uses a stack machine to make it more efficient. But you know, you could write a definition of that machine itself using AirAssembly, and then the programs against that machine would be written in whatever language. You know, let's say you could write a definition of TinyRAM processor using AirAssembly, and then you would write programs in whatever language the TinyRAM processor would understand. So it's kind of a lower level than that, I would say.
I see, thank you.
Mm-hmm.
Are there other questions, clarifying questions before we move to a broader discussion?
What was the name of this machine you said you were working on?
It's called dstuff. You know, if you go to this to the GitHub Guild of Weavers, it would be one of the projects there. It's in the very early alpha stage. I just released it last week.
Thanks.
When in a prover, for example, what would the typical time taken to generate the execution trace relative to the time taken for the cryptographic operations be?
When you generate a proof, I mean, it depends on the specific program, but in most cases, like unless you have something crazy complex, the time taken to generate execution traces is nearly negligible compared to FFTs that you have to run. So I think, you know, just giving a few examples on dstuff, and there are some benchmarks if you go to dstuff. It's a fairly complicated, you know, much more complicated transition function than MIMC. And in there, you know, let's say if I generate a proof for a specific size of the computation, it could take 2 seconds. Out of that, about 100 milliseconds is taken up by generating the execution trace, and maybe 300 milliseconds are taken by evaluating constraints. So like 75 or 80% is taken up by running FFTs, combining the constraints into a composition polynomial and so forth. So it's and you know, a lot of this is also, yeah.
It's kind of similar to witness computation in R1CS-based systems. Or,
yep.
Yeah. Okay.
More questions? Okay, so one discussion topic I'd like to raise. So as far as I know, this is maybe the first standardization proposal of roughly, I guess, a front end, which takes some programmer specified computation and kind of turns it into an intermediate representation that can then be fed into a backend. So I was hoping that we could talk about people's thoughts on front ends and what aspects of them might be worth standardizing, just the, where front ends and the standardization effort intersect. So I'd just like to open the floor to if anyone has comments on that more broadly.
Hello, yeah, so my take it is that this seems very specific to a very particular proof system, which I think is good for what you're trying to do. But I'm wondering whether we could be slightly more abstract and general. Like I lack intuition, but my feeling is that there is something happening here that makes batching, for instance, easier. So you evaluate the same function f all the time for each transition step, so that makes batching easier. And I think that many proof systems exploit that, not just Starks. So maybe there's something more general that we could do.
I would say it's definitely very specific, because I targeted AIR specifically, and as far as I know, Starks are the only systems that use AIR as the underlying constraint system. I'm not sure if there are any other systems that would rely on AIR, just at least at this point in time. But I would be curious. I don't think answer myself whether the same technique would be applicable outside of AIR, but I would be very curious to learn about it.
Yeah, I think this notion of leveraging, structured computations that are kind of doing the same thing over and over again for benefits, whether it's avoiding pre-processing for the verifier or optimizations to make the prover run faster or something. This is a recurring theme kind of in the research literature. And it's a very interesting question whether something can actually be standardized, as opposed to just being an idea that is kind of well known to the protocol designers out there. So worth thinking about for sure.
I mean, so I talked earlier about similarities with Plonk. I mean, it's not so much that it's similar to a specific Plonk circuit, but maybe it's similar to a turbo Plonk configuration where you're specifying a set of gates and selectors and polynomial constraints that apply to those gates. That's actually very similar to what you're doing here.
So maybe I wanted to add, some perspective on the question about specific versus generic. So let's maybe go back and see historically what happened for circuits / R1CS. So traditionally, cryptographers typically build proof systems directly for Boolean circuits or arithmetic circuits. This is kind of what was the state of the art, not state of the art, but just what people do, say 15, 20 years ago. And then there were several proof systems where it turned out that it was particularly convenient to go a little bit higher up and talk about generalization of circuits, or R1CS. And it just happened to have been natural in many settings, both for pre-processing snarks with universal setup, pre-processing snarks with specific setup, transparent snarks that handle circuits. So it was more like an empirical, emergent, useful language across many designs, across different types of cryptography. And so kind of R1CS seems to be particularly useful in that respect. I think something similar has yet to happen for machine-like computations. you can design proof systems for machine-learning computations for, pairing-based snarks, for discrete log-based snarks, for hash-based snarks, which are starks in this case. And so when these efforts will come to pass in these different settings, I'm confident there will be like some common structure we can just pull out and say, look, this is like a good enough common structure for all these settings, kind of analogous to R1CS. It may maybe exactly like Air, maybe Air prime. And of course, at high level, all these things are just machine computations of some sort that happen to explicitly talk about fields and non-determinism. But yeah, so I think I myself been interested to see kind of what is the ultimate Air formulation that will work for kind of all future proof systems. And I just think that's kind of a bit more of an empirical statement that we have yet to see in the next few years. Then maybe we'll come back and see a slightly better level of abstraction than is sort of good enough for most proof systems. There is not a need to tailor it. By the way, if you go back to all the proof systems that do use R1CS, you can choose to tailor the language to the proof system underneath and forego R1CS. There is always something you can be more efficient and make it more specific to the underlying proof system. Yet we choose to stop at R1CS for sanity's sake, right?
And even with AirAssembly, so there is one thing that I'm kind of trying to think through whether it makes more sense or makes sense to do that. As I mentioned, like there are different parts of this modules, and a transition function, technically, it's not really Air. It's not really part of Air definition. It's just there to help you generate a trace table. But in theory, like if you can generate trace table in whichever way, you could do it like using anything. And then as long as your constraints hold on that table, that's what matters. Here it is done so that you can just put everything in a single place. Your transition function described using the same language as constraint evaluations, but it's really what constraint evaluations, that's what matters for, that's where the actual Air is. It's the description of the constraints.
So on that topic, if you were just to optimize how the transition function is expressed, you would still have the same Air, and you could just do that optimization on the previous side, and the verifier would still be compatible with it.
Yeah, exactly. So the verifier, actually, the way it works, it doesn't even read the transition function. All it cares about is the constraint evaluator. The transition function is there purely for the approver to generate the execution trace. And that execution trace, it's actually one of the things, there is a trade-off between kind of efficiency versus the ability to describe it in a uniform way. So the way you describe a transition function using AirAssembly is not the most efficient way. Because it's probably much more efficient to describe it as a, let's say, a Rust program that generates some two-dimensional matrix, and then you apply constraints to it. So you could gain potentially some efficiency, but because the actual evaluation or building of the trace table is such a small portion of the overall time, I kind of decided to put it inside the AirAssembly. But for me, it's still an open question. Do you want to have the transition function described as part of this definition, or do you want to say, you build an execution trace table in whichever way, and then you have to just describe the constraints that have to hold on that execution trace?
Because another approach to this would be, rather than having a language, to have an API to construct errors, and the same relationship as there is between, say, Bellman and Snarky or Socrates.
Yeah, I think that could work too. And there is another open question for me. So right now, AirAssembly itself is not really composable. So you can have like AirAssembly defines a specific computation, but you can't say like call a function from one AirAssembly module, from another AirAssembly module. And the way I've been trying to handle composition, which is still, I think, is a fairly challenging task, is at a higher level language. So like AirScript, which compiles into AirAssembly. It allows you to take several AirAssembly modules and then it compiles them into a single AirAssembly module. So it kind of like I try to handle composition error constraints on that level, but it's not clear to me that's the best way to handle it, to be honest. And you have to go through a lot of trade-offs when you do that.
So is that basically adding new registers that control whether a given module is switched on or off in parts of the computation? Is that how it works?
In a way, yes. So it kind of like, you know, if you think about, let's say, combining transition functions or combining transition constraints, you have to introduce an extra register and says, like, at this point, you want to use transition function from this module. In the different step, you will use a transition function from a different module.
If you do that, are you basically, is there some inefficiency involved from the fact that you're not using all of the registers in all of the modules? So you presumably have to choose the number of registers to be the maximum number that's needed by any module.
Yeah, I mean, there are different techniques to optimize for that, and that's kind of going into a very complex territory. But yeah, so there are inefficiencies, and I would say inefficiencies they don't necessarily come from the number of registers, but every time you apply a switching function, every time you kind of have an extra condition, you raise the degree of the transition function constraints, because you have this multiplication that happens like by 1 or 0 or whatever, but that raises your degree, and the higher your degree is, the kind of longer, the bigger the proof will be, the longer it will take the prover to run. So that's the biggest issue with composition, that it raises the degree of the computation. But at the same time, you can get to a fairly high degree, like degree 8 allows you to take 256 execution paths, or have 256 individual transition functions, so to say, that you can apply in different steps. So
I see, because you can, each one can be a Boolean, and you can just
exactly
Booleans. Okay, I see.
Yeah.
So I think this is a fascinating question, the one of composition. So let's kind of see the analogy first with R1CS or circuits. If you have two pieces of a circuit or two gadgets of R1CS that you want to throw together and let them be part of the same description of the computation, all you really need to do is to identify which variables are shared between the two. So it's a pretty kind of low overhead composition. You just say, look, this variable actually happens to be this one in this gadget and this one in this other gadget. And so now they are part of the same computation description. But you had almost no restrictions on how the circuit and R1CS looks like. So no wonder throwing them together is an easy kind of operation.
And not only easy to implement, it's semantically very clean, because
yes,
the composition.
Exactly. Yeah.
Yeah.
However, if you start saying, well, I don't want a computation that is generic. I want a computation that has lots of structure, because I want to exploit this structure by saying that the description of computation is much smaller than describe the computation, right? So now suddenly you have an issue of like, okay, if I have some heterogeneity in the computation, because I'm sort of trying to put together two different types of computation, now you have to decide, okay, am I sharing register? Am I doubling number of registers and allocating the left for one and the right for the other? How often are they repeating? Is it like for every 5th step of the first computation, I do 1 step of the second type of computation? So these are rather annoying. And in normal kind of computation, our computers, we always have assembly code, but we have the aid of a very generous operating system to manage kind of different processes for us. And of course, one solution would be to say, well, just write like a minimal operating system and then express your computations within it. But now you have simulation overheads. You have like some outer process that is managing the inner processes, and you pay for that simulation overhead. So balancing these two things and finding what is the, I don't know, barely minimal compositional infrastructure that lets you sort of programmatically and semantically put together programs in a way that doesn't cost too much overhead? I think it's a very nice question because, you know, in this racket, we pay a lot for every gate that we pay for, much more than every cycle that goes through a processor. Therefore, we have to be very, very stingy in the type of infrastructure we set up to put together computations. I think it's a very interesting question, and I think has yet to be solved.
Yeah. And I tried, so like with AirScript, I tried to do the composition, but to be honest, the way it worked out, it's still very limiting, and it's actually not as clean as I would like it to be. So it's a difficult question. I agree.
Can you say a little bit about what led you to kind of create the AirAssembly language at the level, meaning high level versus low level? I'm kind of getting at user-friendly, like programmability, you know, at the level you set it at. So, you know, rather than like writing a C program, this seems a little harder than that. I'm guessing there are efficiency benefits you're maybe deriving from having it be a little less usable. That's the trade-off.
So it's actually interesting how I started. So I started actually with AirScript, which is a higher level language. And I first implemented that, and you know, to make things simpler in AirScript, I started to adding features to the language, which, you know, syntactically make a lot of sense. It's easier to express different things, but they add a lot of like complexity on the background. And then when I tried to think about how would I merge the, let's say, two different computations defined in AirScript, there is a lot of overhead, not necessarily overhead, but there is a lot of complexity associated with each specific construct of the language. So what I kind of decided to do is go to the minimal amount of like constructs that you need to be able to express air, and that was the AirAssembly. Like this is kind of almost the minimum things that you need to express the computation. While AirScript, as an example, has much more that you can do, like you can define, you know, different loops and if statements and all of that stuff, which you know make programming easier. But at the same time, if you don't have this low-level bare minimum representation, it makes like trying to think about composability almost impossible. I mean, it's difficult with AirAssembly as it is, but with AirScript, thinking about how do you compose two programs written in AirScript was even much more complicated. So I decided to do this like bare minimums, kind of like only the necessary constructs, and then see if the composition would be easier at that level.
And sorry, AirScript, just to confirm, AirScript outputs AirAssembly code?
Correctly. AirScript compiles into AirAssembly.
Okay.
I'm going to just say something. I think that for me, the AirAssembly process strongly resembles hardware compilation, where it would produce a net list of gates and multiplexers and things like that. And you were talking about the size of the system that comes out after you've compiled your AirAssembly. It's very much resembles the process of netlist size minimization. So I think there's been a lot of work done absolutely outside the crypto world at reducing the sizes of netlists of gates.
Yeah, I would, I mean, I think there's a lot of similarities with actually hardware design in some ways in there, because you kind of think about switching and turning off different registers or like different functions or instructions in different states. And it leads to thinking about how you would design a processor. So like tiny RAM, I think, is one example. Like this stuff is another example, which basically is a processor that uses, switches on and off different instructions. So there are a lot of similarities with the hardware design.
Yeah, but what I wanted to say is there's been quite a lot worked on from various levels of higher level language to automatic or assisted optimization, because with the crypto, you've got the issue of this kind of great big explosion in the size of your circuit, which is a problem later. And maybe some of the work done in the hardware world might be helpful for reducing the size of that.
Yeah, I think this is a great research direction in general, to try to leverage techniques developed over in the hardware world. And obviously the cost benefits, the costs of proof systems are different than the cost of, I don't know, some chip out there. But I think that probably deserves more attention. Good research goal.
And on that point, the main metrics in air, one of course is the size of the execution trace. So basically the bigger this matrix is, the number of registers by the number of time steps, then so the bigger a computation you're trying to prove, so you want to minimize that. But that's not the only thing. You also have the kind of complexity of the transition constraints connecting two states. And there, an important parameter that just doesn't show up as much in kind of real world computers is the degree. So you want to submit, you're going to pay multiplicatively in that degree. So, so it's a pretty hefty price. That's why often you try to kind of maybe allocate more registers and flatten the degree to something smaller, because you pay multiplicative in that. So most efficient air constructions will have a degree that you're rarely going to go above, 3, 4, 5, 6, 7, something like that. Something one has to be like very, and this is just an artifact of the underlying proof system. You could easily imagine just defining like a toy, I don't know, algebraic machine to play with, and just doesn't care about the degree of the transition constraints connecting the consecutive states. Yeah. So I wanted to kind of maybe steer the discussion a little bit towards the artifact, namely the document that Bobbin prepared for the community. I think sort of course, there is this presentation, and we get around to talk about and ask questions to Bobbin directly and get to hear nice answers. But then there's also the artifact itself, and sort of, I guess probably Justin and I are interested to hear the opinion of the community in terms of the draft that describes this AirAssembly. In which direction should it go? Like, one could imagine a number of directions. One can always ask, please put in more examples, maybe. Another direction could be, please compare with alternatives, so the community in the meantime could try to understand better the trade-offs. By alternatives could mean sort of some of the thoughts around the comparison with TinyRAM and the fact that this is more lower level than a small processor. It could be maybe pointing out how, I'm not sure. So I'm actually unsure myself, looking at them and asking the question to the community also. We haven't really done much front-end standardization.
So I guess maybe one thing I can say, I mean, I'm not definitely not an expert in front-ends nor on AirAssembly, but one thing I could say is that we've been in the previous discussions, a lot of the focus was on like how to sort of abstract the protocol and look at the primitives from a different angle and things like this. And maybe a question to ask here is whether we would like to have some maybe like examples that are explicit gadgets, or gadgets. I don't know if you can call them gadgets in this case because they're actually computations, but specific primitives that are exemplified as a given in the AirAssembly format, right? And then we would be, again, kind of going back maybe to what Dara was saying in the previous session to focus on maybe commitments and see how that would look like across different standards and working groups.
I'm happy to provide, like, if there is a specific set of gadgets, like I have some already kind of expressed in AirAssembly, like Poseidon hash function, the rescue hash function, and things like that. But if there is anything more than that, I'm happy to provide if it will help. I mean, I think my goal with this is to get to a point where I'd like to see, like, there are several start proving systems out there, and I'm trying to think how a proof generated on one system can be verified on another system. I know like GenStark is one, Starkware has has another, 0x has another prover verifier, and they all kind of have probably, I mean, I know for sure they have different representations internally of how they think, represent computations. And it would be, from my standpoint, hugely useful if, the different start proving systems could understand the same language. But the language needs to be powerful enough where it shouldn't compromise on performance, so that it's useful and makes sense for them to use that language. So I think from my standpoint, like I would still like to understand like if there is anything missing or if there is anything that is extraneous that could be removed so that other proving systems could adopt something like that.
Well, personally, I learned how Stark worked thanks to this library, the Air script, and playing with it. And I found particularly interesting every time I could see an example of how to do the MIMC or just Pedersen commitments, or just, I don't know, or the Fibonacci sequence, or all these small things, or maybe not so small examples. And that can also help you not only understand how to use this library, but understanding stars as well. So, but I completely agree with Daniel that such a well, standard or guide, or call it whatever this document, this one should have some appendix with some examples so people can understand, this way of thinking or this way of designing programs for stars. And I mean, any relation or any repetitive piece of gadget that could be applied in a larger, I don't know.
So there are going to be some primitives that it's possible to implement efficiently in either Starks or R1CS or Plonk or that kind of proving system. And some that are sort of optimized for particular systems. How do we organize that in the standard? Because it looks to me as though the standard is going to be huge. So it will need some care and attention to organizing it in a way that is reasonably accessible and just doesn't.
Is it possible? Like, I mean, maybe there are just too different of the systems to have a single standard. Maybe there, R1CS type systems can use one standard, and like Air type systems could use another standard. I'm not sure if it's not like if the task of trying to combine and come up with something standard for both types of system is maybe insurmountable, or at least huge.
So I want to maybe I agree. So I wouldn't know where to start. I also want to say that we should distinguish two things: the language and the front end. So both R1CS and the Air language can be very succinctly, or at least very concisely, expressed as kind of interfaces offered by the proof system. Right now, we're discussing not so much the interface, but we're discussing the front end that reduces some basically DSL down to it. So, like the comparison here to R1CS is how would we standardize some DSL for R1CS? And for such a document that nobody has proposed yet, it would also involve some kind of non-trivial amount of discussions, because you're spelling out some DSL for a programmer or some or as a backend for some other compiler, right? That is richer necessarily or more usable than directly writing R1CS. So it will maybe include some types. It will not just field elements, but like vectors and matrices, like Bobbin has. So like it will be like non-trivial. It's not like a concise, cute sort of language and you go home. Like it seems like it has a lot of knobs to things to play around with. So it's really about the DSL.
Are we even attempting to do that on the R1CS side? Because there are many languages that you could imagine compiling to R1CS. I thought we were basically just standardizing the interface rather than front-end languages as such.
We're not attempting. I mean, I'm not aware of anybody attempting to do it. Also, it's kind of but at the same time, the problem landscape is slightly simpler in the sense that many people understand R1CS, rather clearly, and also many people have come up with their own sort of a homegrown DSLs, and then either they just use them themselves, or they just open them to the community for others to also use. One should also note that the fragmentation of DSLs that compile down to R1CS exists, and maybe it's not necessarily a good thing. Maybe one could make an effort to come up with a pretty good DSL that is actually useful to most people. And if we were in such a world, then maybe it would be worth it to spend some time making it more precise and spelled out somewhere. I'm not saying that I'm encouraging that we could. I'm saying that that effort would be possibly of similar complexity as the discussions around AirAssembly, because it is a DSL for a simpler language. Plus additional complications.
I kind of think that having 3 or 4 actively developed DSLs, which is basically what we have, is almost optimal, because you have some competition between them. They can take different approaches. They're developed by different groups of people, so you have some redundancy. Yeah.
Fine. So maybe the question that we should ask is if ZKProofs as an entity has something to do with AirAssembly as a front end, then what role should it play with these 3 or 4 front ends for R1CS, if any? Kind of that could be one way to sharpen the goals out of these types of discussions.
So on the R1CS side, the attitude has been as following so far. Because there's such a proliferation of different front ends, and because almost any major user of R1CS has decided to build their own rather than use the previous ones due to differences in tastes and requirements, it seemed like a very difficult task to achieve any kind of unification and force people to drop their customized homegrown solutions. Instead, the focus has been on enabling interoperability between the different front ends. Of course, at the level of the raw R1CS represented as flat files that came out of ZKProof 1, but later on through the ZK interface proposal. But the approach of ZK interface is basically a calling convention that enables different front ends to interoperate and collaborate in creating a constraint system, and also in populating the variable assignments, that is both the instance reduction and witness reduction parts, while maintaining complete agnosticism about the details of the front ends, which language it is in, what level of abstraction it is in. Basically, we have a calling convention that allows chunks of R1CS constraints or variables to be passed around in a way that allows semantics to be attached but doesn't enforce it. So the good news is that this actually seems to work well. We now have adapters for multiple popular frontends, both as consumers and as producers of chunks of R1CS. There are some very nice demos demonstrating this interoperability, including some running in browser. The challenging part of adapting this approach is that it relies on the fact that R1CS is very shallow. It does not have any structure, and that allows the composition of chunks to be done relatively easily. However, for Air, with these algebraic constraints that explicitly exploit the fact that there are repeating elements and patterns in the topology, it seems much more difficult to come up with the right abstraction that would allow that kind of calling convention procedural interoperability. So I pose this as something to think about.
We don't have to do it in the same way for Air and for R1CS.
I have a question concerning this, and more as a user of this kind of system, and not from argumenting from the inside. R1CS looks to me like a combinatorial circuit in hardware design, and on the other hand, Air looks to me more like a clocked circuit. And my ASIC design software understands both of it, and we need both of it because a general computer has both of it. So why this dichotomy? I don't get why we stick with this. I know where it comes from, but does it has to stay like that? Because quite frankly, I'm not caring if it's R1CS or Air from a user perspective.
I mean, if you use a commit and proof approach, then you can glue together an Air circuit and an R1CS based proving system circuit. That works fine.
Yeah,
what do the others think?
Sorry, I didn't hear that.
Yeah, I'm interested in the opinion of the others as well, because I'm still not seeing why this dichotomy has to prevail.
So I think one reason you see this kind of dichotomy come up is that an R1CS system that's totally unstructured inherently is going to, the verifier is going to have to read the whole R1CS system. So you can't avoid that expensive step. So these proof systems that use Air, they're trying to avoid that. So they need more structure in this intermediate representation than an arbitrary R1CS system has. But you can also consider R1CS systems that have analogous structure baked in which case the dichotomy goes away, and it's just, at that point we're just talking about, you know, which intermediate representation various backend proof systems like to use. I hope that made some sense.
Plonk already is not just an unstructured bag of constraints, because you can have gates that refer to relative to the current row.
So regarding the dichotomy, so there is I guess a theory paper that co-authored with several wonderful colleagues last year that maybe flew a little bit under the radar because it's mostly a theory paper. But in it, we defined this notion of succinct R1CS, which is, you imagine your R1CS matrices are kind of block diagonal and have this kind of staircase matrix that looks like a transition function. And you can imagine a proof system that gets sort of several kind of matrices. Some of them are unstructured, some of them are structured. And you can have one proof system and even one specification to talk about kind of smoothly about a kind of arbitrary matrices. And if they happen to have structure, then you exploit them and you don't have to like read them in full. And if they have no structure, then you just read the no structure part. And that gives you like a pretty smooth connection between the machines and the circuits world. So, yeah.
I mean, there's always a trade-off between waiting for the right abstraction and just standardizing what you have already. I think we're probably at the point where we should just standardize what we have already. And that will be useful even if we find a better abstraction, because the better abstraction is going to be a generalization probably.
Maybe the question then is also, if we standardize what we already have, is how do we make sure that we're standardizing so that it's sort of flexible enough so that later on we can abstract it easily, and right, people don't need to re-implement things from scratch, both for our R1CS and for our assembly, right?
So here we are nearing the end of the allotted time, and maybe we should ask if there are some more questions for Bobbin or points of discussion.
I'd like to say something just about that dichotomy again. I think that the sort of sequential thinking that I'm seeing in the AirAssembly there and in Air versus R1CS kind of circuit building, even with various kind of structure, it does tend to or at least in other domains I'm thinking of, it tends to lead you to produce different styles of circuits. It sort of facilitates a different kind of thinking. And I'm imagining that the effective circuit complexity and degree was mentioned as well, will actually turn out to be different with those different styles of thinking. I suspect that the two can be completely sort of translated backwards and forwards with some difficulty. I'm not completely sure that that's easy to automate. And you may well find that if you assume that both representations are simply equivalent, that they're not necessarily equivalent in terms of what they can easily facilitate for various proofs and complexities and things like that.
Yeah, I think that's true. In trying to optimize Planck circuits, you do have to think differently based on the sort of, it's more of a layout oriented style of thinking, because it matters which rows are next to each other. So yeah, that's actually very different from R1CS. But even though you can translate R1CS into Planck and vice versa, as you say.
I can almost imagine having subroutines in one that are called from the other, and that is sometimes a useful abstraction to work with.
There's a, it's better to think of relations than functions. We're used to thinking of calling functions in conventional programming. But what we're building here is constraint systems, and calling relations is a much more natural abstraction, I think.
I agree with you. By function, I was.
Sorry, yeah.
I meant function as we can see on the screen at the moment, which isn't,
right,
really a function when it's expanded. It's, of course, it's more like a macro in a constraint system.
Right. I think we're at the end of the session time.
Okay.
We are indeed at the end of session time. So then we should warmly thank Bobbin for submitting his proposal to this event and giving such an informative and clear presentation, and also to the participants to this discussion and listeners. So thank you all.
Thank you.
I would like to say thank you to the moderators, thank everyone, including Yael, who I think left earlier. But again, I would just want to remind to everybody who's interested to join the working group for this session, given that there is a lot of topics that need further discussion and figuring out the direction of such a potential standard. Right? So yeah, thank you all. As usual, I'm going to stop recording now. And
thank you, Daniel.
Thank you.
Thank you, Dara. And thank you to Anais for note-taking, and Dara and Markov as well for earlier.